Hi there, welcome back to my channel. Today I have what I think is a very nice treat for you, which is the explanation of an optimization model found in the wild, more specifically found in the hit Netflix series Suits. I know, this series has been around for a long time. I believe it started or premiered in 2011. I'm just getting to it now. It's 2023. But I started watching it recently, and first of all, I love it. It's amazing. I even brought this up in class, and a lot of my students said, yeah, I watched this. It's awesome. So it's a very successful series from my understanding. And as I was watching episode 8 of season 1, it just so happens that they encountered an optimization problem. And I want to point that out to you and explain what's going on and actually show you how they could have used, an optimization model and Excel to solve it. In the episode, they don't explain how they solved the problem, but they state the problem. So let's take a look and see what happened. Right? So if you go, it's around 35 minutes into episode 8 of season 1, you will see, Harvey, Mike, and Lewis in Harvey's office. And they're trying to track some money that got stolen from the endowment of a charity. And the exact amount of money that was stolen was this: $152,375,242.18. So this money was, they assume, transferred to some sort of fiscal paradise in Liechtenstein, right? In Liechtenstein, they have 16 banks. So they were trying to kind of look at all the deposits made to one of these 16 banks on a specific date. That was the date in question. Now, they brought in Lewis because of his financial expertise, and he was able to narrow down from the 16 banks to just 5 of them, okay? And he explains in the episode why he ruled out the other 11 banks, and he had plausible reasons to do so. So Mike and Harvey were like, yeah, that makes sense. So now the question becomes, okay, we need to be looking for a combination of accounts among these 5 banks that had deposits on that day. Because as Lewis explains in the episode, when people are trying to hide money like this, they don't just make one transfer. They take the amount and split it into several smaller amounts and deposit them in different banks, the accounts of which, of course, are all owned by the same person, right? So then the idea is this: okay, Mike says, how do we figure out which accounts are his, right? Since he took this money and split it. And the idea that Lewis comes up with, well, they're all gonna add up to the exact amount, the 152 million, and so and so. That is to say, can we get a list of the deposits made that day, of all the deposits made to those 5 banks, and find a collection of small deposits that when you add them up, they equal exactly the amount of money that was stolen, right? And then they later make a comment, well, this is a simple law of mathematics, right? If you broke something into pieces, the pieces have to add up back to the original. So he said, so we just have to figure out a combination of accounts. Exactly. So this just should be in quotes, because this problem is a very well-known problem in the world of computer science, and it's called the subset sum problem. It's quite difficult to solve, especially if the final amount is a large number and you have a large collection of small amounts. Again, as I said, they don't show it. So at this point, they cut the scene and only show them afterwards with the result in hand. They did figure out a combination of accounts that had deposits adding up to the 152 million. But how did they figure this out? How did they compute this, right? I'm going to show you one possible way. And here's the idea. So let me open my Excel here. And I have, a little explanation of what's happening here. And I generated, let's say for the sake of the example, there were 50 deposits made to those 5 banks on the date in question. So I generated here in this column B 50 random numbers of deposits, right? And the question now is, okay, I need to figure out a combination of a subset of these 50 that adds up to the exact amount that we're looking for, right? So my decision is, should this be one of them, right? So for each of the deposits that I have listed in front of me, I need to answer the following question. Should I pick this one as a deposit that will be in my collection? That is to say, I can create 50 yes-no variables, which we learned they're binary variables, right? They either take the value 0 to say no or 1 to say yes. So I'm creating next to each deposit one binary variable. So I have 50 of them here. Say I want you, solver, to pick for me some combination of these guys, a subset of them, so that when I add up their values, they sum up to what I'm looking for. Okay? Now, if I do a sum product, right, between the column of deposits, right? And part of my Excel is slow because I'm recording the screen and then it kind of overloads the computer. So I take a sum product between the deposits, right, and my yes/no variables. I'm simply multiplying each number by an x. So let's say I have x's from 1 to 50. If the x says yes, meaning it's equal to 1, right, it means I picked that deposit as part of my collection. So 1 times the number gets me the number. Yes, I want this number. Or the x will be a 0, saying 0 times anything is a 0, meaning I don't want that number, right? So if I do that here, hit enter, as I start putting values, oh, what if I pick this guy and this guy and this guy? You see that this number starts to grow because I'm picking them. And the exercise is, can you find places to put ones in here so that you match exactly this amount? Now, if you were to do this by hand, it would take a very long time, right? So the idea is I don't want to do this by hand. I want the solver to find it for me. So, but this is what's going to be happening. The solver will be picking places to put a 1 here for you. Great. Now, to limit this search, I'm going to add an extra constraint and say, okay, probably there weren't more than 9 accounts or 9 deposits that can achieve this sum. So I'm going to say, if I sum these yes/no variables, whenever you sum binary variables, you're basically counting how many of them are equal to yes. And let me delete this one from here. So if I sum them, I'm going to say, okay, this is how many yeses you had. I don't want to use more than 9. All right, great. So I could, in principle, just run the optimization like this and say, minimize this number here, find me the least combination of accounts so that this equal that. Now, for technical reasons that I don't have time to explain here, it's gonna be faster for the solver to solve this problem if I approach it from a different perspective. And let me show you what that is. Ideally, right, I would like the difference between these two numbers to be 0, right? If the difference between them is 0, it means I matched. So let me do this. As the search is proceeding, this number could be approaching the final number from below or from above, right? So let me compute 2 differences. One of them is this number minus that number. And the other difference is going to be the opposite. It's going to be the second number minus the first number. Okay? Notice that at any point in time, this difference is either going to be positive or negative, right? If what I picked is too much, I overshot, one of them is going to be positive because it's going to be the larger minus the smaller. And if I undershot, the one that was positive before now becomes negative because my attempt is now smaller than the target. But at any point in time, as I'm looking for an answer, one of these differences will be positive and one will be negative, but they'll be equal in value, in absolute value, right? So what I really am looking for is I would like to push the absolute value of this difference to 0, right? And the way to do that in an optimization model while maintaining linearity, as in not using the absolute value function, is to do this. You compute two differences, a minus b, and then b minus a. And then you create a new variable that is going to be, this variable is going to be the largest of the two differences. And the largest of the two differences is going to be the positive one. And I want to push this largest difference down, right? So the z variable is going to be equal to the largest difference. And this largest difference is going to be either positive or negative. All right? So when I'm setting up the optimization, here's what I'm going to do. I'll go into our solver friend and say, great. My objective is going to be, I want to push down this z, this amount, which is the largest of the two differences. I want that to be 0, because when that reach that point, I have matched the numbers. So I'm going to minimize that. And my variables will be, well, I have these 50 guys, right, to pick or not. And I also have this z guy, because the largest difference is initially unknown to me. So there is a variable, even though I know what I want its final value to be. Because it's possible that it won't find an answer, right? If I picked the wrong collection of deposits, which means they might go back and say, you know what, I dropped that bank, let's bring that in because among these, we didn't find a combination. Great. So I want to know which yes, no's to pick, and I want to minimize the difference so that it matches. Constraint-wise, what we're going to do is this. We're going to say, great, I want to use no more than 9 accounts. So accounts used at the most, accounts available. And to make this, pushing the difference down to work, I need the following trick. I have to say, okay, if z is the largest of the differences, it means it is larger than both of them. So z is larger than difference 1. Notice at any point in time, difference 1 could be positive or negative. And z also has to be larger than difference 2. Right? So if this z amount is larger than both of them, it is larger than the largest of them. And as I push z down, I am pushing both of the differences down, all the way to a null value, a 0 value, right? Great. So if I do that, the last thing I need to do now is to tell solver, by the way, these variables are not quantities or fractions or anything like that. They are actually yes-no decisions. Should I pick this deposit as a member of my collection of deposits? So I'm imposing the binary condition on these cells. So now we're ready to go. One more detail. This is a linear problem. And whenever you have binary or integer variables, you should check your options to make sure that you're not ignoring integrality. If you want the true best solution, you should put a 0 here. And automatic scaling is probably a good idea for this problem because there's a combination of very large and very small numbers involved. So this is all set for me. Click OK. And finally, we could just click Solve. I'm not going to do that here because this problem actually takes several minutes to solve. but I'm gonna just close. I showed you how to set the solver up, and I have a solved tab here. Notice that we did manage to get to 0. This is identical to that. We used 9 accounts, and here they are. So if the pick RES for deposit 3, 11, 15, 24, 30, 31, 34, 40, 42, they do add up to exactly $152,375,242.18, and we have caught our thief. So this is how the folks in the Suits series could have managed to solve this problem. I hope you enjoyed this example. I had a lot of fun with it when I was watching the episode. I'm like, man, I have to make a sheet for this. So just to show you that optimization is everywhere. It's fun and it's useful. Thank you for watching. Hope to see you guys here again for the next video. Bye bye for now.